All right. Wait, is this? All right. So, um, today we're gonna be talking about momentum, and really what it is, what it means, and the equations, and how momentum is related to. Later, we're gonna talk about impulse. So, how momentum could change over time. So, all right. So, momentum is given to us by the equation. Uh, P P is the variable that we use to denote momentum. E equals mass times velocity. Now, velocity is a vector quantity. We're gonna put an arrow over that, and because momentum is a scalar, you're multiplying a scalar by a vector. That means that momentum is also a vector. Now, our units here, mass is given to us in kilograms, and then velocity is given to us by meters per second. I mean, our units for momentum are kilogram meters per second. Now, momentum is a very common thing that we use in our day-to-day life. Like say we have a ball rolling down a hill. The ball starts up here, goes through the motion, and ends down here. Ends at call it x final, starts at x initial. So take a ball rolling down a hill. Um, at the top, we would say that the ball doesn't really have a lot of momentum. And at the bottom, we would say ball has a lot of momentum. Now we could show that with an equation. Let's say the ball was starting at rest here. Means our v initial equals 0 meters per second, and then it has some v final at the bottom. So we would say that because it has no initial speed at the top and it rolls down and gains no speed at the bottom, that the ball gained a lot of momentum. But this equation up here doesn't really refer to change in momentum. So how can we get to change momentum? So another way to think about momentum is the force that it takes to stop something. Like, you see something coming at you, like the ball, for example. The ball is rolling towards you, and you're just like, oh, how much force do I need to stop that movement? Like take a car rolling down the road. And so here we have a car rolling down a road, just a regular road, so it has friction on it. Um, and then initially the car has some velocity. Now let's say the car wants to reach zero velocity by the time it reaches this final point here. And its braking point, the point where it starts using its brakes, is x naught. So the car is coasting, and then once it goes through this point right here, x naught, then the car applies its brakes and stops. Let's say we have a graph of force with respect to time. So we have force on our y-axis and then time on our x-axis. And let's say this graph represents how much the force with respect to time required to, like the force applied by the brakes with respect to time, seconds required for the car to come to a complete stop. So you can either have a really big force, but it wouldn't take that much time. Like the car slams on its brakes, it would stop pretty fast. It's a lot of force applied, but it wouldn't take that long for it to stop. Or you can have or you can have a small force applied for a longer time. You know, the the um the car applies its brakes for like very gently, and the car slowly slows down. But it takes a lot of time. But it's a minimum force. So clearly, force and time have some sort of relationship affecting um the uh the momentum of the car. The car is a given momentum at x naught, and clearly, as we just illustrated, force and time have some sort of relationship to momentum. This relationship, we can actually derive it from Newton's second law. We have F equals ma, where force is a vector and acceleration is a vector. Now recall, a is acceleration. Acceleration is velocity with respect to time, the derivative of velocity with respect to time. So we can rewrite this as m dv over dt. Uh, and once again, v is a vector quantity there. We can write this as f is a vector, dt equals m dv as a vector. Now let's try integrating both sides. So we would have the integral from t initial to t final times force is a vector with respect to t equals, because mass is a constant, we don't need to include that in our integral. So we equals mass, the integral from velocity initial to velocity final with respect to velocity. Now, let's just leave this alone here for a second, and let's focus on this. We can actually rewrite this as um, m times, because there's nothing in this integral, times velocity final minus velocity initial. So let's rewrite this again. Uh, the integral with respect to, or the integral from t initial to t final of force with respect to time. We can actually rewrite this if we factor out this, or if we not factor out, if we use the distributive property to multiply this mass in to the VF minus VI, we can rewrite this as MVF minus MVI. Now you may notice, if you look at from earlier, our equation for momentum was mass times velocity, and because we know that momentum is conserved, we can actually turn this into um, PV momentum final minus P initial. And, well, once again, that equals, if we turn this integral into F delta P, force is a vector, and these are all vectors except for time. So, yeah, I know I did a lot there, but we went from force equals mass times acceleration to force equals mass times the derivative of velocity with respect to time. We moved the dt over to the same side as the f. So it was rearranged to be force is a vector times dt equals m times dv as a vector. And then from there we integrated. So we had the integral from t initial to t final of force as a vector with respect to time equals the integral of velocity initial to velocity final with respect to velocity times mass. Remember, we could pull mass out because mass is a constant, so we don't need to include it in our integral. It's not changing. And we can actually rewrite this part of the integral as mass times velocity final minus velocity initial. And then if we use the distributive property to multiply that mass into those parentheses, then we can rewrite it as the same integral equals mass final velocity minus mass times initial velocity. And recall from earlier, momentum is mass times velocity. So we can rewrite this part as uh, momentum final minus momentum initial. Both these are vectors. Sorry, I should have included that. So we can rewrite this as momentum final minus momentum initial equals force times delta t. For a constant force, it's force times delta t. And we can actually rewrite this part here as change or delta p, and these are all as vectors. You know, momentum here is as a vector, force is as a vector, and change momentum is as a vector. So we have change momentum equals force times time. Now we actually have a special name for this, and it's called impulse. we use the notation J. And once again, J equals, as I just said over there, J equals change in momentum as a vector times uh, the constant force times delta T. And this is given to us in Newton seconds because force is in newtons and times in seconds, so it's in Newton seconds. So we have impulse, which is change momentum, which is equal to force times change in time. And then we can further illustrate the relationship between impulse and momentum by rewriting this part here, by taking this part here and saying that J equals momentum, J equals momentum final minus momentum initial. Now, if we add the momentum initial to both sides, we can rewrite this as momentum final equals impulse plus momentum initial. So back to the car example. This equation illustrates the relationship between the initial momentum of the car and the force applied by the brakes. Because remember, J is force over time, or force times time. So it's the force of the brakes over the time that it broke. And because the forces are going in opposite direction of the car's velocity, that means that force is a negative, or force is going in the opposite direction and times time. That means that J here will be, for our car example, J would be negative, which makes sense because we have our positive initial momentum because momentum is a vector, so it has direction. And because velocity was going to the right, we established that our right was positive. And then we have J here just illustrates how the brakes slow down the car. So we have the force applied by the brakes over the time that the brakes over times the time that the brakes were applied equals momentum final, which for our car example would be zero. So that's just a brief summary of how momentum or how impulse is derived. How So that was just a brief summary of what momentum is and how it relates to impulse, how impulse is derived, and how it relates to real life examples like a ball rolling down a hill or a car coming to a stop on a road with friction. All right, thank you for watching. Have a good one.